This video is about engine combustion and how it relates to power with different changes of the squish band. This graph out here represents a general idea of how the combustion expansion force happens. As the gasoline burns, it expands due to heat, and that expansion is what pushes on the piston. And so the maximum, this represents the maximum force right here. So it gradually goes up and then gradually goes down. So probably this is the maximum number of gasoline molecules burning at once. So that expansion force works in conjunction with the volume above the piston. This being TDC right here, you can see it's the lowest amount of volume, okay? And as the crank rotates and the piston goes lower, you have more and more volume, okay? That volume and the force work together to make the combustion pressure. And the reason you have the peak right here is because you have such small volume right here. And you've got a rising combustion force, which causes the rate of increase of pressure to be more than the rate of expansion force. And it peaks right as it starts to change and expand, increase that volume more. And that combustion pressure works on the crank to rotate it, okay? And these two graphs do not look the same because at top dead center, there is no power transferred to the crank to aid its rotary force because the conrod is vertical. So the farther you get down here towards 70 or 75 degrees, the more you can see that the two are almost equal here. So yeah, if there was a way to move that pressure way over here, that would be super excellent. But because of the rate of volume increase due to the piston movement, it just is what it is. That peak pressure is always going to happen between 10 and 15 degrees after top dead center, always. So I wanted to understand the process even more in depth, and so I created a spreadsheet that incorporates the ability to read the actually to create the pressure graph according to the expansion force graph, and then for that pressure graph, the crank rotational force graph. And then as I change that graph, notice what the changes are here at the crank. And so the first test I did, or the first comparison I did, was moving this more to the left. You can see right here, it's a little bit oddly shaped, with the peak happening more to the left, maybe about 12 degrees more to the left. And now we're going to compare the two crank power graphs right here. And the result is only a 0.7% increase in crank force. These two are almost equal. Increasing the squish velocity increased the power at the crank early, but made it worse late. So next, I changed the I shifted this whole graph over by 5 degrees to start at 10 degrees before top dead center instead of 15, which is basically retarding the ignition, which is what you have to do when you when you increase the squish velocity very much. So let's compare that and we have that right here, and the difference is a 7% increase in overall power at the crank. So the lesson learned here is if you're going to increase the squish velocity by reducing the squish clearance, you're going to have to also play with the ignition timing to get that right. Just to retard it and try different settings with it retarded. So this spreadsheet is free on my website. Look at the description of the video to get that. If you just want to see the details of how I derived those figures. So the lessons learned is you can gain power by increasing the switch velocity only if you retard the ignition. Without retarding it, the power will stay the same. Peak combustion pressure will always be between 10 and 15 degrees, no matter what you do. The expanding force of combustion does not reduce to zero before exhaust port opening, which means you could be wasting significant force if the duration of force is too long due to too much squish volume, mostly due to excessive squish area. What I'm saying on that last one is, if you look at the graph here, you'll see the degrees after top dead center, okay? If you have an 180 degree exhaust duration, that means all these graphs get thrown to zero right at 90 degrees, right there. And you can see that the crank force is pretty low by that time. It's about 1/6 of the peak. Okay, but let's imagine this combustion force graph shifted over here to the right because it's got too much squish volume, which delays the burning of the mixture, which shifts this whole process to the right, which also gives more power late to the crank. But if that happens and then it's just cut off by the port opening, that's a mismatch. The idea is to have that squish volume in relation to your port duration. The higher that exhaust port is, the quicker you want everything to happen, which means a smaller squish area, a smaller squish clearance. Yeah, you got to have everything related to each other in the correct way if you want maximum power. So last but not least, I wanted to test what the difference was if I were to shift this where it goes low earlier, not there, but over here, keeping the same amount of energy, which would increase the peak here. And so this is what I did with this graph. Okay, right here, it peaks higher and then goes down, and that's to match, to be a better match to 180 degree exhaust duration, because you still got all that energy right there, and then the exhaust port opens and just everything just goes to zero then. So comparing the green and the purple graphs of the combustion force, combustion pressure, and crank force, I also get a 7% increase. So that explains previously why the increasing the squish velocity helps, and then decreasing the squish volume, if it's needed, helps. If you If you don't need it and you do it, that probably would be a power loss. So going by my website and the graph that I show, it gives you the idea whether or not you're going to be close or way out of the ballpark for your exhaust duration and what you have with your squish area. So that's it. That's not a whole lot to say on this subject. Just it's nice to be able to graph it out and use formulas and stuff to clarify, because we all start off with ideas and what it should do, and making these kind of calculators just helps to verify that the idea is right on or not. And that's what I did. At first I was like, oh crap, increasing the squish velocity doesn't hardly increases the power at all, 0.7%. And then I said, well, you know, um, probably needs to retard the timing. So that's what I did. And sure enough, that made the difference and got it up to 7% increase. So anyway, yeah, just follow the links in the description, which also leads to my page about squish velocity, squish clearance, squish area, and my squish calculator. Thanks for watching.